Good morning again. Still in electricity and magnetism. Today we need to talk about Unit 3, discussing magnetism and electromagnetism. Today we discuss what is a magnet, magnetic field, magnetic force, and electromagnetic induction. Magnet. A magnet is a piece of material with a strong attraction to another metal object. This strong attraction of a magnet is called the magnetic field. Then every magnet has two poles, a north pole and a south pole. Rules for magnetic poles is that like poles repel each other and unlike poles attract each other. Let us consider two bar magnets. In figure A, we have opposite poles which are near each other. Let us take the north pole of the first magnet to be near the south pole of the second magnet. These two poles will attract each other. Then unlike poles attract each other. And if we take a south pole of first magnet and approach it to the north pole of the second magnet, the two magnets will attract each other because unlike poles attract each other. In figure B, we have other two magnets where the north pole of the first magnet is near the north pole of the second magnet. The two magnets will repel each other, means they will push against one another. Then this happens if you take the south pole of the first magnet and approach it to the south pole of the second magnet. The two magnets will repel each other because like poles repel. Then here comes that law of magnetic poles, which states that unlike poles attract each other while like poles repel each other. Then here we have a diagram showing that a magnet can attract and magnetize the objects made of iron, such as a nail. The magnetic field and a magnetic force. A magnetic field is a region surrounding a magnet where the magnet can exert its property of magnetism, which means that the magnetic field is a region where the magnet can exert its force of attraction towards other pieces of metals. Here we consider a bar magnet and consider the compass needles, which is are put near this bar magnet. The orientation of these compass needles shows the orientation of the magnetic field lines. Actually, the magnetic field lines leave the north pole and they enter the south pole. The number of magnetic field lines leaving the north pole is equal to the number of magnetic field entering the south pole. If we consider two bar magnets where like poles are approaching near each other, then the magnetic field lines they will all leave the north pole, means that they cannot enter from one magnet to another, but they will create a neutral point between the magnetic fields of the two magnets, because these two magnets repel each other. But for attracting magnets, means that magnets whose unlike poles are approaching near each other, magnetic field will leave the north pole of the first magnet and they will enter the south pole of the second magnet, because unlike poles attract each other. This means that there is a strong magnetic field between the two bar magnets. And the magnetic force, let us consider a particle having a charge Q that moves in a static magnetic field of strength B with a velocity v. The strength of the force on that charged particle is equal to is proportional to the magnitude of the velocity, the charge Q, the magnetic field B, and the sine of an angle theta, which is an angle between vector velocity and the direction of magnetic field. Then the this magnetic force is given by a vector quantity as F equals Q V vector B. We know the definition of vector product. The definition of vector product gives magnitude of the first vector times the magnitude of the second vector times the sine of an angle between the two vectors. Then the magnitude of the magnetic force is Fb, which is equal to absolute value of the charge times the magnitude of the velocity, which is the speed, times the magnetic field, which is also positive, times sine of an angle between vector velocity and the magnetic field, or simply F equals QVB sin theta, where this magnetic force may be 0 when theta is equal to 0 degrees or 180 degrees. This is when the vector velocity is parallel or antiparallel to magnetic field. And this magnetic force is maximum, has maximum value when theta is equal to 90 degrees. This means that sine of 90 degrees is equal to 0. This is when vector velocity is perpendicular to magnetic field. And the magnetic field is equal to the force, magnetic force divided by the charge v speed sine theta, where the unit of magnetic field is called Tesla, where 1 Tesla is equal to the unit of force Newton divided by the unit of charge Coulomb times the unit of speed meter per second. Then we know that Coulomb per second is equal to the unit of current ampere. It's the reason why this unit of magnetic field, which is Tesla, is equal to Newton per Coulomb meter per second, which is equal to Newton per ampere meter. And here we have an example of calculation. An electron in a television picture tube moves toward the front of the cube with a speed of 8 times 10 to the power 6 meter per second along the x-axis. Surrounding the neck of the tube are the coils of wire that create a magnetic field of magnitude 0.025 Tesla, directed at an angle of 60 degrees to the x-axis and lying in the xy plane. Calculate the magnetic force on and the acceleration of the electron. Here to find, we have a diagram showing it. We have the direction of the speed. The speed equals 8 times 10 to the power 6 meter per second. The speed is given v, and we are given magnetic field B, and we are given the angle. We actually know that the magnetic force Fb is equal to absolute value of the charge times the speed times the magnetic field times sine of an angle which is between the vector velocity and the magnetic field. Here theta is equal to 60 degrees, which is an angle between the vector velocity v and the vector magnetic field. And here the charge, you may have a question about the charge. The charge here is the charge of electron, which is equal to minus E, which is equal to minus 1.6 times 10 to power minus 19 coulomb, because we are given that an electron is in a television. So from here we need to deduce the charge of electron. Then the charge is given, the speed is given, magnetic field is given, and theta is given. We are asked to determine the magnetic force and the acceleration. Here the magnetic force equals QVB sin theta. Q 1.6 times 10 to power minus 19, V 8 times 10 to power 6, and B 0.025 theta 60 degrees, where we have this magnetic force to be 2.8 times 10 to power minus 14 newtons. To determine the acceleration, we need to use Newton's second law, where the sum of forces acting on a body is equal to the mass times the acceleration. This means that force that we calculate, which is equal to 2.8 times 10 to the power minus 14 Newton, is equal to the mass of electron times the acceleration. The force is calculated in some question A. The mass of electron is given to be 9.11 times 10 to the power minus 31 kilogram. Then take the force, the magnetic force, divided by the mass of electron to obtain the acceleration to be 3.1 times 10 to the power 16 meter per second squared. In example number 2, we have a beam of proton where the charge of proton Q equals 1.6 times 10 to the power minus 19 coulombs moves at a speed of 3 times 10 to the power 5 meter per second through a uniform magnetic field of 2 Tesla directed along the positive z-axis as shown in this diagram. Here we are given an angle which is between vector velocity and the vector magnetic field equals 30 degrees. Find the force on the proton. The magnetic force on the proton, this is equal to the charge times the speed times the magnetic field times the sine of an angle theta, which is between the vector velocity and the magnetic field. The charge is given, the speed is given, this is the speed V, and this is the charge Q is given, and the magnetic field is given 2 Tesla, and the angle theta is given to be 30 degrees. What is remaining is the numerical application, which gives that F equals QVB sin theta 1, which is equal to 1.6 times 10 to the power minus 19 coulomb times 3 times 10 to the power 5 meter per second times 2 Tesla times sin 30, which is equal to 4.8 times 10 to the power minus 14 newtons. Then motion of a charged particle in a magnetic field. Here we consider a case of a charged particle moving through a uniform magnetic field in a circular trajectory, that the direction of the particle's velocity v is perpendicular to the magnetic field as shown in this diagram. We have these crosses show that we have a uniform magnetic field B, and the charge Q is allowed to move in this magnetic field along a circular trajectory. The speed is always tangent to the curve, and then here we'll see that magnetic force. We see that the magnetic force B. Let me wait a moment. The rule states that once this body is moving in this magnetic field, there is a magnetic force FB, which is acting on this particle, which is equal to the charge times the speed of the charged particle times the magnetic field in which the particle is moving. Then here times the sine of an angle which is between the speed, this is an angle theta, which is an angle between the speed and the magnetic field. Here it is said that the particle's velocity v is perpendicular to the magnetic field b. The particle's velocity v is perpendicular. This means that the angle theta, which is an angle between the vector velocity and the magnetic field, this angle is equal to 90 degrees. Then we need to consider this situation by considering that this angle is equal to 90 degrees, where sine of theta is equal to 1. Then this magnetic force on this charged particle equals to QVB. And the particle maintains a circular trajectory. To maintain a circular trajectory, there is a force which is called normal force or centripetal force acting on this particle. This centripetal force is a force that allowing the particle to maintain its circular trajectory. This is equal to the mass of this particle times the acceleration called centripetal acceleration. This centripetal acceleration is studied it in circular motion and the rotational motion equals to the square of the speed divided by the radius of the circle. Then here it is said that the magnetic force on the particle is equal to the centripetal force. This is the rule. Then why do we consider this rule? It's because in here we'll have that QVB equals mv squared divided by r. In this equality, will be determining either the charge that is moving in this magnetic field, or it's the speed of the charge, or the magnetic field, or the mass of the charge, or the distance from the center to the circumference, which is the radius. Then we have such a situation where the force F equals QVB equals to the centripetal force mv squared over r. This gives that this radius r equals mv over qb. Then since the particle can make a complete circle, and since the period of its uniform circular motion equals 2 pi r over v, and we have seen that r is equal to mv divided by qb. Do you see? Then by replacing r into this expression, we see that the period of uniform circular motion is equal to pi m over qb. Pi is always equal to 3.14, and m is the mass. This is the mass of a particle. Q is the charge. This is the charge, and B is the magnetic field. This is the magnetic field, and the V and V is the speed, where T is the period. The period of uniform circular motion means the time taken by the moving body to move or to make a complete revolution or a complete circle. This means that the frequency, which is equal to the inverse of the period, equals QB divided by 2 pi m. Then here period and the frequency don't depend on the particle's speed. Here we have an example of calculation. A proton moving perpendicular to a uniform magnetic field. A proton is moving in a circular orbit of radius 14 cm in a uniform magnetic field B 0.35 Tesla perpendicular to the velocity. The magnetic field is perpendicular to the velocity. This means that the angle theta is equal to 90 degrees and the sin theta is equal to 1. Find the linear speed of the proton. We are asked to determine the linear speed. Once we are given the proton, the charge here is equal to the charge of a proton. Charge of a proton equals 1.6 times 10 to power minus 19 coulombs. Then we need to apply the formula. We know that QVB, the magnetic force, is equal to mv squared divided by r, which is the centripetal force. Then this square simplifies with this v, and we have QB is equal to mv divided by r. We are asked to determine the linear speed v. The linear speed v is equal to QB r divided by m. This is equal to the linear speed v. The charge q is the charge of proton 1.6 times 10 to the power minus 19 times the magnetic field is 0.35 Tesla times the radius 14 times 10 to the power minus 2 meter divided by the mass. This is the mass of proton, which is equal to 1.67 times 10 to the power minus 27 kilogram. Then this linear speed becomes 4.7 times 10 to the power 6 meter per second. Then if an electron moves in a direction perpendicular to the same magnetic field, we have the same magnetic field, and the charge becomes the charge of electron, and the mass of electron equals to 9.11 times 10 to power minus 31 kilogram. And the charge of equals to the same charge of proton. We are asked and the radius of the circular trajectory if the speed is equal to 4.7. Then to determine the radius from this formula, the radius r is equal to mv, mass times the speed, divided by qb, then which is equal to mass means 9.11 times 10 to the power minus 31, then multiplied by the calculated speed of 4.7 times 10 to power 6 divided by the charge of electron 1.6 times 10 to power minus 19 coulomb times magnetic field of 0.35 Tesla. Then we calculate this radius to be equal 7.6 times 10 to the power minus 5 meters. Then another exercise number 2. In an experiment designed to measure the magnitude of a uniform magnetic field, electrons are accelerated. The particles we have are electrons. The charge of electron is known. Electrons are accelerated from rest. To be accelerated from rest means that initial velocity is equal to 0 through a potential difference of 350 volts. The electrons travel along a curved path because the magnetic force exerted on them and the radius of the path is measured to be 7.5 centimeter, as shown in this diagram. If the magnetic field is perpendicular to the beam, what is the magnitude of the field? We are asking to find the magnetic field strength. Here we use the same principle where we have a QVB is equal to mv squared over r. And then here we have the kinetic energy. The kinetic energy is equal to the net work done here, and then here this allows us to determine the speed, and then or to find the square of the speed. And here we are given that QB equals mv divided by r. We are given electrons. This is the mass of electron and this is the charge of electron. We are asked to find the B. B is equal to mass of electron times the speed divided by the charge of electron, then times r. Here the mass of electron is known. Mass of electron is known to be 9.11 times 10 to power minus 31 kilogram, and the charge of electron is known to be 1.6 times 10 to power minus 19 coulomb, and the radius is given to be 7.5 centimeters, which is equal to 0.075 meters. The unknown here is the speed, and this is the final speed. We are given that initial speed is equal to 0, and we are given the potential difference. Remember what we learned in electrostatics. In electrostatics, we learned that the network is equal to the change in kinetic energy, and this work done is equal to the charge times the electric field times the distance, where electric field times distance is equal to the potential difference V. This means that here we have the charge of electron times the potential difference, which is equal to the network, and the change in kinetic energy is equal to final kinetic energy 1/2 mv squared minus 1/2 mv0 squared. And here this one is equal to 0 because V0 is equal to 0. And then this is the same mass of electron. From here we see that this QE, charge of electron, times the potential difference, it is given to be 350 volts, is equal to 1 over 2 mass of electron times the speed of electron squared. The question mark here is the speed because this charge of electron is given, the potential difference V is given, mass of electron is known, we may calculate the speed. If we calculate the speed, here the speed V will be equal to square root of 2 times the charge of electron times the electric potential difference divided by the mass of electron. After calculating the speed by using this formula, we may then replace the speed in the general formula to determine the magnetic field B. And then this is step 1 and this is step 2 in numerical calculation. And then we have the speed V equals the square root of 2 times the charge of electron, potential difference over mass of electron, which is equal to 1.11 times 10 to the power 7 meter per second, and the magnetic field B equals the mass of electron times speed divided by charge of electron times the radius, which is equal to 8.4 times 10 to the power minus 4 Tesla. Then B, what is the angular speed? The angular speed omega is calculated as the linear speed divided by the radius, equals 1.11 times 10 to the power 7 meter per second divided by the radius is given to be 0.075 meters, which is equal to 1.5 times 10 to the power 8 radian per second. To determine the period, it is very easy because we know that the period T is the time taken to cross a complete revolution, equals to that complete revolution 2 pi divided by the angular speed omega. Then pi equals 3.14, then omega is calculated here, then you get the period to be 43 nanosecond. Nanosecond, 1 nanosecond is equal to 10 to the power minus 9 second. Then this period is equal to 43 times 10 to the power minus 9 second. And the exercise number 3, a magnetic field exerts a force of 8 times 10 to the power minus 14 Newton toward the west on a proton moving vertically, then upward at a speed of, we are given the magnetic force, we are given the speed, and it is said the magnetic field is towards the west and the proton moves vertically upward. This means that the magnetic field is also a vector perpendicular to the vector velocity and the vector force. When moving horizontally in a northerly direction, the force on the proton is 0. Determine the magnitude of the magnetic field B. We are asked to determine the magnetic field where the charge is equal to. The magnetic field is B is Q. We first write QVB is equal to mv squared over r, where we have B is equal to mv divided by qr. The mass is the mass of electron. The speed is given. The charge is given to be the charge of electron or proton. Here given the charge of proton, and the mass is the mass of proton, 1.67 times 10 to the power minus 27 kilogram. And here we need to find this distance r, and then determine the magnetic field. Or here we may use the formula that QVB is equal to the magnetic force, and then B is equal to this magnetic force, which divided by the charge times the speed, where the charge is given to be the charge of proton, and the speed is given of the proton, and the magnetic force is given, and then we perform direct calculation, where the magnetic field becomes 0.10 Tesla. The last exercise, an electron of charge 1.6 times 10 to the power minus 19 coulomb travels at a speed of 2 times 10 to the power 7 meter per second in a plane perpendicular to a uniform magnetic field of 0.010 Tesla. Describe its path quantitatively if the mass of the electron is 9.1 times 10 to the power minus 31 kilogram. The description of the path taken by this electron means this radius r is equal to what? Here we need to consider that QVB is equal to mv squared over r, which gives that QB is equal to mv over r, and then we are asked to find r, where r is equal to mv divided by qb. And here it is said an electron, this is the mass of electron. Mass of electron is given. The speed is given. The charge is given. The magnetic field is given. We perform numerical calculation as shown. QVB equals mv squared over r, r equals mv over qb, and we replace mass, speed, charge, and magnetic field by their values, and we obtain that this radius r equals 1.1 times 10 to the power minus 2 meter, which is equal 1.1 centimeter. And the last point that we need to talk about is the Faraday's law of induction. Then to see how an electromotive force can be induced by charging magnetic field, we consider a loop of wire connected to a galvanometer. Then here, if you move this magnet, let us say move this magnet inside this loop to the left, the galvanometer will deflect to the right. If you stop moving this magnet, the galvanometer needle deflects back to 0. And then if you move the magnet to the right, the needle of the galvanometer moves to the left. This indicates that a changing magnetic field produces a changing magnetic flux, which creates or which induces a current which deflects in the opposite direction. means changing the direction of the magnet's motion changes the direction of the current induced by that motion of the magnet. Then this is the diagram that Faraday used in order to express his law. Then we consider two loops. There is a primary circuit and a secondary circuit. Here, the two circuits are wires which are connected or which are wound around a strong magnetic material, and the first part is connected to a battery to produce an electric current, the electric current, and the switch is connected. Once the switch is on, the electric current will flow through this circuit on the left, which is called the primary circuit, and then it will induce a magnetic field, or it will create a magnetic field around this iron ring. And since a magnet can also create a current, the current which is created by this magnet, then it will be read by a galvanometer which is connected to the second wire. Then here the Faraday's experiment stated that when the switch in the primary circuit is closed, the galvanometer in the secondary circuit deflects momentarily. It means that the electromotive force induced in the secondary circuit is caused by the changing magnetic field through the secondary coil. And here in this part 1, this is a battery normal diagram. Then the battery is connected. It has two poles, positive and negative poles. The positive pole is connected to the switch, and the negative pole to another wire. Then once the switch and the battery are well connected, the current will flow through the first part, which is called the primary coil or the primary circuit. Then the second coil is wrapped around this iron ring to intensify the magnetic field. Then it produces a secondary circuit. Then once the current is flowing through this primary circuit, there will be a change in magnetic field. This change in magnetic field will induce a current in the second coil or in the second wire. This current will be read by this galvanometer. Then the current which is produced here is called the induced current, and the corresponding electromotive force is called the induced electromotive force. Then Faraday concluded that an electric current can be induced in a circuit, means the secondary circuit, by changing magnetic field, and the induced current exists for only a short time while the magnetic field through the secondary coil is changing. Then the magnetic flux is the last point which will help us to calculate the induced electromotive force. The magnetic flux is considered as a number of magnetic field which enters a given surface area, where the magnetic flux equals to magnetic field times the area times cosine of an angle theta, which is an angle between the magnetic field B and a direction perpendicular to the surface. And then here we see that according to Faraday's law of induction, this induced electromotive force is equal to the opposite of the first derivative of magnetic flux with respect to the time, where the Faraday's law of induction stated that the instantaneous electromotive force induced in a circuit is equal to the rate of change of the magnetic flux through the circuit. Then induced electromotive force is equal and opposite to the time rate of the change of magnetic flux. And this negative sign is explained by the Lenz's law, which indicates that the polarity of this induced electromotive force is such that it produces a current whose magnetic field opposes the change in magnetic flux through the loop. Means the current is opposite to its cause. The cause of this current is the change in magnetic flux. Then we close it by considering this Faraday's law. Electromotive force which is induced is equal to minus d phi b over dt. Phi b means magnetic flux, which is equal to magnetic field times area times cosine of an angle theta between the normal to the plane and the magnetic field. And we are closing this topic. Thank you very much for watching.